Dr. Mallove and Dr. Kunimatsu. Dr. Kunimatsu, please.
Well, good morning, ladies and gentlemen. I'm afraid we worked until very late last night and listened to Russian and Indian activities. But I'd like to open this morning session on time. So we have so-called NHE session for this morning. And I'd like to introduce Mr. Matsui, the head of NHE Center, to tell what actually NHE is briefly. Please, Dr.
Good morning, ladies and gentlemen. Good morning. My name is Makoeto of NHE Center. Well, I know that this conference is to provide you much more scientific academic information than I thought. There will be no time for me because I'm going to speak a little larger the general view of activities. Because this morning session, part of this morning session is time for explanation or introduction of activities. We have 5 presentations this morning, and 4 from our research laboratories, so-called NAD laboratory located in Sapporo, where most of you, I hope, are going to visit this coming Friday. And then the last one is from Dr. Makoeto regarding SRI international research works. And I'm afraid to say that yesterday morning, Mr. Yugami of NEDO has already talked about the outline of the project. Therefore, it may not be necessary. It's a kind of thing. Therefore, I hate to do that. But anyway, just for the confirmation, our project is, the purpose is 2, 3, 4. But the main focus is the confirmation and the demonstration of excess heat. I mean, the microphone. Much more loud. Okay. Well, firstly, excess heat. But we like to have a very rigid confirmation. It doesn't, I mean, just a slight symptom or one experiment, very faint proof is not our purpose. We have to have a very strong one. And well, the second, the third, and the fourth purposes on the overview. So the mechanism and the feasibility of this type of phenomenon as a future energy source, those kind of things. And then again, those setup of our project is already explained yesterday. So the money is our national nation's money. Then comes from the Ministry of International Trade Industry through NEDO and then to us. Then most of the funds flows to the activities in laboratory. And then some, I mean, our activities, part of our activities is closely related to the international collaboration, to the United States and the European peoples. Well, the present programs at laboratories. Firstly, demonstration of excess heat. Main focus is reproducibility and the verification of the reaction product and so forth. And the second big focus is on the material because we think there might be some key factors related materials. And the third program is the database and the other T50 studies. And the fourth is international cooperation. Then this morning we do have four presentations from our laboratory. First two presentations is related to heat, excess heat experiments. First speaker will be Dr. Kamimura. He's going to talk about mostly the result of fuel cell type experiments. And the second one is from Mr. Wota. And then he's going to talk about design and then some results maybe by our pro-calorimetry system. And maybe he may talk about the other results too. The second topic, the third presentation and fourth presentation relates to the materials. And in order to obtain the so-called heat, it is assumed we have to have a high loading of nucleation. Therefore, what we should do to obtain such a material, that's the issue. Then the first topic is the processing and treatment for the high deuterium palladium ratio by Mr. Senju. And then fourthly, the general material behavior of the high loaded palladium materials from Dr. Asami. And then finally, we like to invite Dr. Makuru to talk about XR international activities. This is the way we are going to start this morning. Thank you.
Thank you very much. Dr. Matthew, would you like to have some questions?
No, I don't think so.
No? Okay.
This is not such a academic time.
Okay, and in that case, we go through the individual talks. So the next talk will be the excess heat in fuel cell type cells from pure palladium cathodes, and even at high temperatures. The talk will be given by Mr. Kanura. Please.
Thank you, Chairman. I'm going to be talking about excess heat in fuel cell type cells. We have a fuel cell type electrolysis system in our laboratory, as Mr. Matsui mentioned. At ICCF-6, we reported that excess heat has been detected with fuel cell type system in a few cases, but reproducibility of this excess heat was poor, probably because of the use of many kinds of palladium. However, useful information about palladium rod processing has been obtained. The objective of this study is to improve the ability to acquire higher loading ratio and to improve the reproducibility of excess heat. And this is the content of my presentation. I will explain the layout of the fuel cell type electrolysis system and palladium cathode material and their treatment and our experimental results. I will explain fuel cell type cell briefly. This cell was developed by Dr. Kunimatsu, his chairman of IMRA Japan. This cell has three major features. First is that gas diffusion anode is used, which is based on the fuel cell technology, and the cell is closed cell, and both loading ratio and excess heat are measurable. This is a schematic of the anode and cathode reaction in the cell. the anode and cathode reactions, these expressions respectively. The anode does not generate oxygen gas because the deuterium gas diffuses into the anode. And palladium cathode generates deuterium gas, and load itself is deuterium. And in this probe cell, the loading ratio can be estimated by this expression using measured pressure of deuterium gas and temperature. This figure shows VHS type electrolysis system. And this system has 6 pressurized cells. The palladium samples set at the center of the pressure vessel as a cathode electrode and surrounded by gas diffusion, fuel cell anode. Pressure vessel was filled with 1 mole LiOD electrolyte of 50 milliliter and deuterium gas up to 9 kilogram per square centimeter. 3 thermocouples were used to measure the temperatures of the palladium rod, the electrolyte, and the gas. This figure shows the it shows an example of calibration curve and excess heat. The calibration curve determined with nickel cathode and excess heat estimated from calibration curve. The excess heat was estimated by rise of temperature from the calibration curve. The calibration curve was previously determined using the dummy nickel cathode. The accuracy of excess heat estimation depends mainly on the accuracy of assembling the cell. We evaluated the deviation of the calibration curve and concluded that it was within plus minus 2% in our experiment. This value is plus minus 3 sigma of deviation. Therefore, only a measurement larger than 5% is assumed to be attributed to excess heat generation. This figure is an example of electrolysis current pattern. Current profile for 70 days, 14 days was fixed as the same loading condition. And following that time, the profiles were varied. All the samples were electrolyzed for more than 1.5 months. The current was maintained at 125 milliampere for 6 days after the start of electrolysis, and then current was changed step by step after the stable equilibrium was reached. Because of the temperature became stable with 3 hours after current change. Therefore, excess heat was estimated on the basis of cathode temperature measured 3 hours after a step change in current. A standard process to prepare palladium electrodes was determined based on the first experimental results. The results were palladium rod with high purity and stable grains reach high purity over PV, and grain size and or boundaries may be significant. And cracks on palladium surface very likely inhibit high volume. Therefore, palladium rods were made of 4-9 palladium cast and melted in vacuum and processed in room temperature, and their surfaces were machined away to a depth of 0.2 millimeter. Details of this process will be presented by Dr. Asami in this session. Surface treatment were used to determine their influence on DOPD. The treatments were surface etching in aperture to remove surface defects and to clean the surface, and vacuum annealing to release the stress to repress the grains and to clean the surface by thermal etching. And this table shows the samples for the experiments. 1 untreated samples and 8 various treated samples were used. The etching in aquarella was done before the heat treatment. Both samples etched and were not prepared to examine the effect of etching. The samples were etched for 10 minutes. The annealing was performed for 1 or 10 hours at 850 or 1000 centigrade. This slide shows summary of our experiment result. From the result, it seems that excess heat of 0.35 to 0.7 watt, 7 to 18% of electric input power was measured in only 4 samples annual for 10 hours at either 850 or 1000 centigrade. The DOPD of the samples with excess heat was 0.85 to 0.89, significantly higher than 0.8 attained by the untreated sample. And aperture etching before annealing was not effective in our experiments. This slide is the experimental result for sample number 1 annealed 850 centigrade for 1 hour. Horizontal axis is time, and this axis is excess heat, and this is loading, current density, and input power. In this experiment, the samples have low D/PD and no excess heat. On the other hand, this slide is experimental result for sample number 3, annealed 850 degrees for 10 hours. The current pattern is the same pattern as the sample number 1. This sample achieved D/PD of 0.87 and generates excess heat of 0.7 watt. The excess heat was continuously detected after 2 weeks from the electrolysis start. The excess heat observed in other samples also showed the same trend. This figure shows the loading ratio as a function of current density comparing two samples. The data from 2 weeks after the start of electrolysis and in stable equilibrium were used to calculate this relationship. The D/PD ratio of sample number 1 with no excess heat became lower at higher current density. On the other hand, the sample number D/PD of sample number 3 with excess heat increased or did not decline at high current density supply. as shown in this figure. The red data belong to the samples in which excess heat was observed. The blue data belong to the sample without excess heat. The over-PD for cases in which excess heat was observed tended to increase or remain constant at higher current. On the other hand, the over-PD without excess heat decrease at higher current. And this figure shows the relationship between excess heat and loading ratio. The excess heat of sample number 1 was within ±2%, and we judged it to be no excess heat. Sample number 3 attained higher D over PD 0.84 up to 0.87 and generated over 5% of excess heat. Similar results were obtained for samples annealed at 10th 100 centigrade. Excess heat was only measured for samples annealed for 10 hours. According to these results, the time of 10 hours for annealing was sufficient to recrystallize the grain and to clean the surface by thermal etching. But 1 hour was insufficient in our experiment. This figure shows typical relationship between input power and excess heat in our experiment. The solid line is a quadratic fit using the least square method. The excess heat increased quadratically as the input power corresponding to the surface current density increased. However, these results alone are not sufficient to prove the existence of an anomalous excess energy. Although we have been estimated that the deviation from the calibration curve was less than 5%, as previously mentioned, we cannot rule out the possibility that some other unknown factor might increase the deviation from the calibration curve for the system. And one problem of the fuel system is that the system cannot measure net excess heat directly. Therefore, we believe that the existence of excess heat from paraffin is not proven with this experiment. Conclusion. Paraffin samples with the standard process were tested. The samples were high purity 4,9 paraffin melted in vacuum surface ground and treated surface by surface etching in aperture and vacuum ion. The thermal conditions apparently affected loading ratio and excess heat. Excess heat has been only observed from the samples annealed for 10 hours at both 850 and 10 centigrade. Excess heat was 7 to 18% of electric input power. However, the system cannot measure the net excess heat directly, therefore it remains to confirm the existence of excess heat with the flow calorimetry system. Thank you.
Thank you very much, Dr. Hideo. So, are there any questions? Yes? Dr. Ibarra.
I don't understand why you made a calibration with the nickel, with the nickel cathode, just in view of the fact that nickel might also be providing you with excess heat. Why don't you try platinum? Platinum cathode.
どうしてニッケルなのか、どうしてニッケルなのかっていうとですね、白金であったりとか、
I usually use nickel cathode. First, I use platinum, but
it's not neutral. The nickel cathode is known, at least for some experiments, it's not neutral with respect to the cold fusion phenomenon.
Well, that's another ニッケルはこういうふうにも起こすんじゃないかという話もあるから。
I believe nickel has no cold fusion.
That's not what transpires from experiments. So I think it has been a bad choice. You could have used a platinum cathode, which is known to be neutral, as far as I know.
Our experiments using nickel cathode calibration curve is very stable, and plus minus 2% deviation. And
well, we could spend a lot more time on this subject, but it's time is limited. So, are there any questions? Yes, Tom.
Did you document the impurity content, even though you had 4 nines palladium? Did you document the impurity content even in this high purity palladium for the impurity elements?
Details of material characteristics will be presented by Dr. Asami.
Are there any more questions? Dr. Cherani.
So, just thinking again about the calibration, from my experience, when we use a nickel plate for calibration, several times we get some strange effects in respect to calibration using geometer. So from 92, we decided that the nickel sometimes give a very strange effect and we decided not to use anymore. So we use a gold plate, which is developed, or when we have possibility, platinum plate. So I agree completely with the preparator suggestion, don't use nickel plate, because it gives sometimes very strange effect, so make it more complicated the detection of everything. Especially because the water is not really improved, sometimes like water contamination and so on. Okay, just my suggestion. Thank you.
I will examine this.
Okay, so I think we should go on to the next talk, followed by Mr. Kubota from the development and experiments on the Okamoto system.
Thank you, Chairman. Development and experiment on a local unit system. I'd like to talk about these contents. As Dr. Wainwright is talking, there are weak points as an experiment using the fuel cell calculation system. One, this method is not a direct calorimetric measurement. Two, if the measurement points are moved during cell assembly after the calibration, the accuracy of calibration would be lost. So we think that it's necessary to improve the measurements and confirm the measured success key by other methods. A calorimeter system, such as which has been developed by Stanford Research Institute, provides a direct measurement. So the flow calorimeter system for NHE was designed and developed to confirm the observed excess peak at NHE laboratory. And we call it NHE-FCS. two experimental cells are able to be measured at the same time for one system. The temperature of bus A and bus B is kept at 23 degrees C. The flow rate is about 0.7 grams per second. This figure shows the overall system of MHFCS. Water is sent to bus B using a constant flow rate pump, and passing the experiment cell and flow meter returned to bus A. All data are measured by data match meter, and DMM and power supplies are controlled by personal computer. The data sampling time is typically 60 seconds, and power supplies regulating time is every 10 seconds. This figure shows the experimental cells for type C. All experiments have been performed using this type cell since January 1996. The pressure vessel for electrolysis cell is installed in the vacuum insulator, and during the experiment, a vacuum pump keeps on running. The coolant water enters into here and goes out here. The connecting tubes under these vessels are made of stainless steel. These rods are made of glass fiber and the pressure vessel. The cell is fuel cell type electrolysis cell, composed of a cathode, a gas liquid electrodes, and a pressure vessel. This figure shows the decay of electrolysis cell. Each electrode and electric heater is at these positions. The electric heater is made from coiled nickel wire and sealed by PTFE tubes. This cell has a heat exchange tube in its side, bottom, and power board. Water flows the blue area. The temperature of the inlet and outlet water are measured in the tubes at these points by platinum thermal resistor. To prevent the gas leakage, a metal O-ring is used for the pressure vessels C. Experiments are performed in two steps. First step is a calculation to measure the cell's heat recovery efficiency. To estimate the estimated heat recovery is used for the calculation of excess heat during electrolysis with a palladium cathode. The second step is a palladium electrolysis experiment after the calculation according to the following protocol. The current profile was initially the same as that of the reference conditions. Afterwards, open circuit, hydrocurrent exchanging, and anodic treatment are tried. The method of the calculation of dYPD is same as previously used for the fuel cell type electrolysis system. Excess heat Wx is calculated with the following equation. And now, M is the flow rate, Cp is the specific heat of water, and delta T is the difference between inlet and outlet temperature. And Rho is the heat recovery efficiency, Wt is the total input power. in this equation, m by Cp by delta T is recovery power. In calibration experiments, platinum cathode and electrode heater are used, and the heat recovery of each cell is 0.983 plus minus 0.0014. This figure shows the result of calibration experiment using one type C cell. Red line and total input power. Green is that of electric heater. Blue is that of electrolysis. And black is the heat recovery. During this term, heat input only, and during this term, electrolysis input only. And during this term, the total input power was kept at 10 watts by electrolysis and heater input. In this case, the heat recovery was 0.977. And in this experiment, another heater was assigned for dining excess heater generators at star 1. And the test heater was on supply 0.2 watts for 2 hours by another power supply. This figure shows the calculated result of excess power of small same calibration experiment as before preview figure. Black line is a calculated result of this heat. Looking at star 1, it's found that this calorimeter is capable to detect such value of thermal energy. At this figure, calculated result of excess heat is almost plus minus 0.1 watt, except during the period when the test heater was on. The 3 sigma values of the calculating result of excess heat for each cell was estimated at 0.09 to 0.16 watt. So NHFCS has enough sensitivity to detect excess heat of 0.2 watt at total 10 watt constant condition. Using palladium cathode electrolysis, all experiments have been performed using identical trotter, which showed excess heat in prior fuel cell type electrolysis system experiments. This figure shows the typical result at palladium electrolysis using NHFCS. Red line is the total input power, blue is recovery power, green is a D by PD, pink is electrolysis input power, and black is a calculated result of excess heat. These values show the current density. Here, and here, anodic treatment was dry. In this experiment, the material and treatment of palladium cathode and experimental procedure are identical. They are shown here. DYPD reaches a maximum of 0.82, but decreases at high current density. The calculated result of excess heat were almost 0 watt. And this figure shows the detail about the calculated result of excess heat at same experiment. Excess power is fitted to the right axis in this figure. This way is the first measurement. It presumes that the recovery of heat was unsteady because of the complexity of the heat exchanging tube. Excess heat were almost plus minus 0.1 watt during all over the experiment. So it was decided that excess heat was not observed in this experiment. DYPD reached a maximum of 0.84 in some experiments and 0.89 in one experiment. But in the result from all experiments in this series, excess heat has not been observed. DYPD may be insufficient for excess heat generation. This figure shows the detecting heat of loading at the first of radiometric. During this figure, indicating total heat power was kept at 2 watt constant. This peak of excess power is detecting heat of loading. From this triangle area, the heat loading is calculated 260 joules. Calculating from these parameters, it's 310 joules and close to the result of measurement. Therefore, NHFCS receives more sensitivity at less input like this condition. One possible reason that net excess heat has not been observed is that the experimental conditions have differed in slight details from those of the prior experiments, specifically the temperature of the cathode. This figure shows that the electrolyte temperature versus input power for several experimental cells. The square for black is from the fuel cell type electrolysis system, and the triangle of red is from NHFCS. In the fuel cell type electrolysis system, the electrolyte temperature rises at 10 degrees C per hour from 10 degrees C. However, the temperature of NHFCS electrolyte is exactly 38 degrees C when total input power is kept at 10 watt. It is presumed that the temperature influences the DYPD. A mass flow calorimeter system has been developed to confirm the observed excess heat at the fuel cell type electrolysis system. The heat recovery of NHFCS cells has been measured at 0.983 plus minus 0.014. NHFCS is capable to detect excess heat generation of 0.2 watt, a total 10 watt constant condition. And more sensitivity at detecting the heat of loading is exhibited at less input. All experiments using palladium cathode have been performed using identical protocol, which show excess heat at the fuel cell type electrolysis system. Max dYPD have been 0.84 at some cells and 0.89 at one experiment, but excess heat have not been observed at all experiments. One possible reason is that dYPD may be insufficient for excess heat generation, for temperature differ by the cell design and influences the dYPD. Thank you.
Are there any questions?
I want to give my point of view about the ratio of logging ratio and the excess heat. I think the value varies from about 0.7 to 0.9. I think this is an average value. It may be related volume and surface ratio of used cathode. I think in some local value, local region, the ratio may be greater than unit. Thank
you. 給与率は 0.7 から 0.8いくつだけど、それは平均値で場所によっては、ね、それでもっと高いところがあるんじゃないかという、そういうことなんです。だからもし何かコメントがあれば答えてくれればいいんじゃないですかね。もしそれに対して答えがあれば。
In this experiment, dYPD calculated from the pressure reduction, so it cannot dYPD of part of guidance.
How many times did you run the?
So please speak up by microphone, please.
How many candles did you use? How many runs?
From now, 20 customers.
Are there any more questions?
Would you please tell me the volume of the palladium sample in your experiment and the heat transfer coefficient in your experiment?
Heat recovery coefficient, efficiency. You said heat transfer coefficient.
Transfer coefficient. For example, every watt introduce a temperature difference. How much?
Oh, I see. Okay. 1ワットあたり何度温度が上がるかというそういうことを指したみたいです。
At the cell temperature or the coolant water temperature. This is the cell temperature, electrolyte temperature. The NHS at the ICCF-6 total power kept at 10 watts. So all during the experiment, this temperature heat was kept. Start temperature 23 degrees C. So this 38 1.5 degrees C per hour. Right.
Every watt will increase the temperature by 1.5 degrees.
1ワットあたり何度かということを確認してるんです。1ワットあたり何度上昇したかということをもう一回確認したんですから。
それはthe temperature is cell temperature or cell temperature. This temperature is measured all experiments. We confirm this temperature.
Thank you. We discussed it.
And several palladium volume.
Palladium volume. Palladium volume. Palladium cathode size, this size, 4 mm diameter and 15 lengths.
だからボリュームはいくらですか？
ボリューム。
Okay, please calculate, yeah. 4 mm diameter, 15 millimeter, 5 or 4 times d squared times a.
It's just going to be the weight.
Weight is 3 grams.
3 grams. Okay. I see your comment.
I think it is about 0.3 cc.
Yes.
Yes.
So based on my fine-tuning theory, your fine-tuning parameter is too low to see the excess heat.
I see.
Because your heat conductivity is too high. Your volume is the same as the others, but your heat conductivity is too large. Just like the quickness experiment in Australia. They use the silicone oil to improve the heat conductivity. Then their fine-tuning parameter is too low.
Are there any
please show me again the drawing of your devices. Please show me again the drawing of devices.
Device.
Double box slicer. No. Yes. My question is, what is the most important and difficult point to improve or to attain such high heat recovery efficiency? What is the most important and difficult point? I suppose that outer box, in the inside of the outer box is vacuum. Vacuum or?
Yes, or vacuum.
To suppress the radiation cooling of cooling system. Yeah.
Cooling.
Yeah.
This in this lecture, vacuum.
I see. It is very important point.
That's one important point. Another one point is a measurement point. The accuracy is fluctuation of the temperature. Accuracy is low. But this point is near the bath water. So not influences the bath temperature. So we design.
Thank you.
But I'm afraid time is running out. I'm sorry, sir. I must go on to the next. So the next talk will be a study on material processing and treatment for high lithium volume by the center.
Ladies and gentlemen, I hope to present study of material processing and treatment for high deuterium loading. This paper will present experiment result of material study aimed at obtaining increased higher diffractivity ratio in electrolysis cells. The objective of this study is to determine mean by which the diffractivity ratio can be increased. Many observers report that this is important to determining sought-after results. Ultimately, the maximum diffractivity ratio is dependent upon the manufacturing history of electrodes and the condition of electrolysis. The diffractivity ratio was studied using a resistance measurement method in order to establish a procedure for accepting electrodes, which can be expected to give high diffractivity ratio. In this study, relationship were found for the diffractivity ratio and the following parameter. Heat treatment of palladium electrodes. Electrolysis and current pattern. Cycle of electrolysis. Surface treatment of electrodes. For this study, most of the electrodes what we would use were energy standard palladium. Just we start with 99.99% purity palladium, which were melted and cast in vacuum, and cold work at room temperature. This process will be described by Dr. Alasami after this presentation. Here is a schematic diagram of electrolysis cell and system for resistance measurement used to calculate diffractivity. The 4-point flow measurement made with 1 milliampere 1 kHz AC source. In all 5 platinum wire or spot wire or palladium electrodes. The palladium electrodes were 2 mm in diameter and 15 mm in length. Use 1 more ever of this solution. The diffractivity ratio is an empirical function in alpha zero. We use data previously obtained at SRI for this calculation. This graph shows typical results comparing the effect of different annealing temperature. The green line is corresponds to sample anneal at 1000 degrees C. The red line corresponds to 850 degrees C. And the blue line corresponds to 200 degrees C. The best results were obtained for sample anneal at 1000 degrees C, indicated the electrode heat treated and higher temperature probably yield a higher diffractivity ratio. This figure illustrates the effect of stepwise change in the current density was changed stepwise. The result suggests that there is an advantage that will go current density initially, and then ramping to higher current density. For example, current photon, which starts from 20 milliamperes per centimeter, 1 and 2, give a higher diffraction ratio than the current photon will start at 2000 milliamperes per centimeter. Number 6. Second cycle is more clear this tendency. We also find the better results were obtained by studying at the lower current density than by studying at the higher current density. We have found that tentative hypothesis that deuterium entering at 20 milliamperes per centimeter due to the strong loading were able to diffuse inward. However, deuterium at 200 milliamperes per centimeter were rapidly absorbed near the surface, creating PDD near the surface and destroying the lattice. This interferes with ability to absorb deuterium better. This figure shows that there is a beneficial effect in repeating the current cycle a second and third time. That maximum diffraction ratio is in the first cycle, diffraction is 0.86, where lower than the reach in the second diffraction is 0.9, and the third cycle 0.95. With each repetition of electric cycle, the maximum diffraction ratio were larger than the diffraction ratio reached in the previous cycle. We do a reverse potential of 0.75 voltage after each cycle of electricity. Applying reverse potential of the electrodes backwards were observed to improve diffraction. By this reverse potential, deuterium observed from the surface layer was dissolved and disturbed. So, deuterium decreased in the surface layer. As a result, in the next cycle, deuterium were observed. However, there is still limiting value of the diffraction ratio value for reasons which are not entirely clear. This is the baseline protocol used for studying the effect of surface treatment for cardiac cathode. Heat treatment of energy standard material results in changing the grain size difference between the inner and near surface region. Special treatment for red color products, posing, homogenizing, and modification of grain size. The resultant grain size is 15 micrometer to 100 micrometer, which we consider to be small grain. This is its material, etched cross-section picture. Inner and near surface grain size is near size. the effect of different surface treatment upon the divergence ratio. This treatment includes polishing with diamond grid and etching with agarose for different lengths of time. If cloth etched with agarose show the higher divergence ratio, 0.95, then if cloth polished with diamond grid, 0.94, and 0.92. The surface treatment for extrudes were also observed to have important effect. For example, etching the cathode in accreditation results in higher loading than polishing with diamond grid. Also, short etching time appears to be better than etching for long time. There is several conclusions which based upon the result of this study. If cloth heat treated at higher temperature yield a higher divergence ratio. The divergence ratio can reach a higher value if the initial current density is low. The repetition of the electric cycle results in a loss divergence ratio were reached in the previous cycle. Etching by operation was more effective than polishing for divergence. In the future, we intend to study the effect of graphite and impurity in palladium electrodes on the divergence ratio and other surface and bulk properties. We are preparing to inch measurement system. One is inch microscopic system. It can observe the surface of palladium cathode during elysis through a coarse cell. And this is an elysis with palladium and observe slip band. And another inch to X-range diffraction system, which can measure change in lattice content of palladium through a beryllium window. And this is palladium peak. And in electrolysis, this peak is small, and PDD is in electrolysis peak. We hope to measure much interesting data use this system. Thank you.
Thank you very much. Are there any questions? Yes.
Would you mind showing me on your palladium electrode where you attached your 4-point probes? And did you ever attempt to correlate your resistance measurements with the gravimetric measurements? Or did you just use the SRI curve?
We use SRI curve, but
これと一つは16歩で確かめたかということ。それと6端子はどこにつけたかということです。
Excuse me. And I'm not measuring the wave method. And flow is current is end to end, and voltage in current point to voltage point 5 millimeter difference. Voltage point inside in current point.
Are you okay with this answer? Okay. Are there any more questions? Chairman.
Do you have any explanation why the loading ratio is very, very different with open cell type of experiment and the previous experiment with the closed cell type? Can you think that the recombiner has some deleterious effect on loading? Thank you.
Yes, and this is the open cell. We use only selected electrode and judge the effect.
オープンセルとクローズドセルの違いが大きいけど、それはどうしてかというと、リコンバイナーが何か悪い働きをしているのではないかという、そういうことです。
Yes. Dr. Kamimura mentioned closed and measurement method, pressure method, and because different measure method type, and we now we are not yes, and I have a question, and this point you discuss I understand difference between the methods.
He does know why the data are different in open and closed cells. Yes, there's a question. Yes.
How much etching gives the best results? In other words, how much metal do you remove? 1 micron, 2 micron?
エッジングの程度ですね、表面の厚さ、どれくらいエッジングすれば一番いい結果が出るかと。
10 minutes average 10 minutes etching 200 micron.
200 microns?
Yes, 200 microns.
And what impurities do you think are removed by the etching?
Impurity is on the surface, I think. But because 1 minute etching is okay.
And do you have any idea why too much etching is bad? If you etch more, why is that bad? Do you have any idea?
すぎるとダメなのはどうしてか。今分かるかという。
I think surface square is more big is no good. Excuse me. And not the not and excuse me.
Well, I think the time is running out, so I should go on to the next talk. But I'll ask Professor George Mallove to chair the next two talks.
Thank you. I'm pleased to call for the next paper, which is Material Behavior of Highly Deuterium-Loaded Palladium by Electrolysis by Dr. Singh.
Thank you, Chairman, and good morning, everyone. As last presentation from the energy laboratory, I'd like to talk about material behavior and the characterization of highly deuterium-loaded palladium. It has been pointed out by several observers that achieving high reproducibility of anomalous effect depend upon the producible high deuterium loading. Therefore, material studies have been emphasized in this project. And objectives of these studies to clarify the conditions of material processing and treatment to achieve high deloading, and to observe and analyze material behaviors during electrolysis with palladium deuterium water system. To optimize electrolysis and material conditions, and to define the future material issues in this project. Deuterium loading experiments are carried out with palladium electrode using fuel cell type electrode resistor, which was developed by Japan. And the details of this system was already explained by Dr. Kamimura in the first presentation of this session. This is a schematic figure of the electrolysis cell. And this table shows the material list of palladium sample used in experimental studies. And TKA 399 materials casted in air and cold work mainly by swelling machine. And TKAS is a single crystallized by floating zone method using TKA materials. And TKBS series is a high purity 49 materials casted in vacuum and cold worked
and 0.2 millimeter surface is removed, defective zone. And in this series, many kind of treatment is applied. One is used as cold work, and one is used after 1000 centigrade for 10 hours in vacuum over 10-6 for the top. And other is first aqualasia etching and high temperature and high vacuum annealing. This is a typical history of electrolysis. This curve is current density, and this curve input power, and dotted line temperature. And in this case, loading ratio is changed like this during about 15 days electrolysis. In this case, the maximum attained D/PD ratio is 0.9 at 200 milliampere current density. And here, at higher 800 milliampere current density, the D/PD ratio is attained 0.89. I would like to show you some interesting microstructures. In this case, single crystal after electrolysis. Many regular slip bands along the 111 plane were observed on the surface. And this radius is about 2 micron. And the X-ray diffraction pattern of the post-electrolysis specimen shows the sample no longer is purely single crystals. And in this figure, several internal plaques are observed in the post-electrolysis single crystals specimen as shown in this. And the cause of this type of plaques may be produced by the alpha-beta transition, or you can see the inclusion here. The deuterium accumulated near this surface and pressurized and rapid propagate like this, I suppose. In the high purity materials, 499, the before electrolysis samples, you can see the grain boundaries and very fine structures. These fine structure and grain boundaries may be made by thermal etching at a high temperature and high vacuum state. In the case of after electrolysis, you can see the microplaque along the grain boundaries, and also observe the fine slip band like a single crystal. this structure is shown the rather relatively low loading state. In this case, 0.2. And this here, the cross section of here. And the alpha plus beta phase progress laterally towards the center, or alpha phase shrink towards the center. And also observe the microgranulation is advanced in this alpha plus beta phase. This figure shows deuterium crystalline after the electrolysis. You can see the crystalline here. And the magnified figure of this part is like this. The top of the crystalline also observes plaque along the main boundaries. And of course, we observe the slip band, main slip band. This case, I suppose, some kind of pore or clay-like defects exist near the surface. The materials very soft by the annealing. Then deuterium accumulated in the pore or the plane defects and pressurized over 100 atmosphere and basically occur, I suppose. In this figure, surface impurity analysis shown. Sulfur, chlorine, carbon, nitrogen, oxygen is observed in many samples before and after electrolysis. This was measured by Auger electron spectroscopy. And this figure shows palladium this depth profile. And from the sputtering time, we calculate the depth of this region. Some kind of impurity penetrates from surface. And the depth of this penetration impurity is about 1,000 angstroms. This was confirmed by Sims or Ikegama, and that impurity is identified issue. Well, the basic requirement for capable of achieving a high loading in this table, the favorable material state is basic favorable material state is here, and corresponding treatment. And first is to have large number of vacant absorption sites. And second, to have large absorption area during electrolysis. And third, to minimize dissociation area and prevent incremental loss of deuterium. And post column is to minimize the quantity of dissociated deuterium during the loading, deloading process. Detail is omitted, however, the corresponding treatment is like this. From those basic considerations, corresponding suitable material treatment and reduced as shown in this table. The specification and the treatment of palladium materials having high loading ratio have been selected as follows. Specification of palladium. Initial impurity over 4-9 up. And vacuum method and casting and forging and annealing to homogenize during intermediate state of processing. And after the processing, after the reduction, machining the outer 0.2 millimeter to remove surface defect. This was suggested by Makoeto. And treatment, suitable treatment is surface planing and etching by aqua regia to remove surface impurities. And ultra-high vacuum and high temperature annealing to recrystallize and to activate surface. In table 1s, this and this material series of made on this concept and achieve the highest loading near 0.9 or 0.91. As a further issues, to prevent blistering, plaque formation of at grain boundaries, and to prevent loading reduction at higher current density. And second, to maintain good ductility and resistance against the deformation to the stress release. And finally, to clarify the effects of deposition of impurities, surface impurities, and resume penetration. Thank you.
Thank you. We're running late, but at the risk of having a short coffee break, I certainly want to have questions. Yes. You come to the mic.
Did you observe any evidence for preferential diffusion of lithium along grain boundaries?
The figure is little small. However, you can see the grain boundaries beta phase propagate like this. For example, this part is more faster than in the brain. The brain boundary is little effect to promote the alpha to beta transition. I think.
My question was like diffusion of lithium.
Answer. Lithium.
Did the wave boundaries help to diffuse the lithium into the cathode?
Yeah. I don't know where, but the lattice distorted by lithium. The distorted lattice maybe promote diffusion and general sense, I think.
Yes.
You mentioned that the deuterium ions can go to the orthohedral position up to unity loading. Is there any evidence that you can get tetrahedral loading? I mean, when they're in orthohedral loading, the separation between deuterium ions is 2.74 angstroms. Is there any evidence you go to tetrahedral loading when the separation is reduced to 1.74 angstroms?
Dr. Morrison, will you repeat your question more slowly? He doesn't understand. Thank you.
O サイトから T サイトへの変換。
In your talk, you mentioned that orthohedral sites were occupied up to unity loading. My question is there any evidence that you can get tetrahedral sites being occupied?
T oxide or T site?
Tetrahedral, yes.
I think as you pointed out, I think the T site is seems to be acted as transient site. We measure by pressure in this case. So the average, averagely, we cannot measure the local loading. So the averagely, the loading ratio is not over 1 unit. So I think this site is a transient site.
We can take one more question. Yes.
According to your conclusion,
yes,
the palladium cathode, shape of your palladium cathode is not suitable to attain such a high loading ratio. Don't you think so?
What is suitable shape?
Yes, but maybe the load is not good for keep the stable state of palladium in such a heavy electrolysis. So because you have some non-homogeneous piece along with how to say center and
yes. I think for get more high loading in short time, the signal is the best, or smaller size is the best for get short time high loading. However, in our standard case, we use 4 millimeter diameter and 20 millimeter length. We confirm by standard sample.
I can understand. Your such a rod shape was selected before your good conclusion. Okay?
Thank you.
Thank you. I'm afraid due to the time we need to continue this discussion in the coffee break. Thank you, Dr. Asami, for a good presentation.
To begin by making some introductory remarks, remind you of the hypothesis, the phenomenological model that we're chasing here in this field. And I want to focus very closely on the issue of replicability. To me, it's the central issue. We must get control of our experiments in order to make reasonable progress in a reasonable time frame. And a plea for perhaps better coordination than we have achieved historically. In our experiments at SRI, we've obviously attempted to replicate our own previous published results. We've worked with Ben Bush to try and replicate the Miles Bush heat helium results, with Chino Srinivasan to work with the nickel light water systems. We have worked on the Fleischmann-Pons boil-off experiment, and I presented that yesterday in a poster. Working a little bit with Ed Storms to test his protocol and concepts for pre-test of palladium materials for their suitability. And we're doing some work with Jim Patterson and SETI, and I have a poster and a small presentation this afternoon discussing those matters. This talk is actually largely a sales pitch to go to a number of other presentations and a number of other posters on our collaborators, various and many. One of the things, and Fran Tanzella will talk to this point in much more detail, one of the things that we've focused a great deal of effort on recently, just because of the difficulty in replicating, reproducing our experiments, is the fundamental issues of electrochemical kinetics, mechanisms of hydrogen discharge, interfacial impedance studies to interrogate the kinetic processes, an issue that Martin Fleischmann has made great issue of and has been largely, I hesitate to say ignored because one can't simply ignore Martin, but his advice hasn't really been listened to, the search for hidden state variables in the experiments that all of us are doing. There is at least uncontrolled variable, perhaps more than one. We simply have not come to grips with that variable. Surface films play a very important role. We've heard a great deal of discussion this morning and yesterday about loading, the difficulties of obtaining and maintaining loading. Surface films, adventitious surface films, which form in part because of the impurities that are present in the experiments. Very, very important. We've tried to look at the structure and electrical properties of these films. We've identified critical roles for two elements, silicon and lithium. We've looked at the effect of ultrasonics in removing the films, how it affects the overvoltage, and how it affects the loading. And if you talk to Dr. Tanzella, he will talk a little bit to these points, more than I have time to do here. Something that we've become much more interested in recently, not because I have any special interest in thermodynamics, but because it happens to be important. Thermodynamics of metal hydrogen systems, making overvoltage measurements, the significance of high hydrogen activity. What does it mean to have a very, in fact, extremely high activity of hydrogen in the metal lattice? One of the things it does clearly, as Fukai has pointed out ably and in many publications, introduces a special character, special defect character into the lattice. This may very well have important properties relating to cold fusion experiments, relating to other experiments, more fundamental issues. Question of endothermic loading, and the concept of a phonon laser somewhat associated with these defects, Fukai defects or other defects, and I direct you to Peter Hagelstein's poster for what I think is a very important contribution to the understanding of theory in this area. There are metallurgical concerns, and our collaborators here in Sapporo are doing very good things, very important sterling work in understanding the metallurgical issues associated with irreproducibility of the palladium. I've said this before, I've said it and said it, I'll say it again. Our hypothesis, based upon observation of our own and others' experimental results, phenomenological model, to observe anomalous, what we call excess heat, you need to achieve and maintain a deuterium to palladium loading at or above some critical value. You need to attain it and maintain it for a considerable period of time, several hundred hours for 3 millimeter palladium cathodes, at currents which are significant, hundreds of milliamps per square centimeter or hundreds of milliamps. We're not quite sure if this is a current or a current density criteria. And we've erected, and I presented at Monte Carlo a little model, phenomenological model. Excess power is related to some constant, current above a threshold, loading above a threshold, possibly to the second power, and some flux criteria. There must be some variability of the loading, some flux of deuterium through the interface. We are simply trying to test that hypothesis. We're trying to do experiments to achieve those conditions so that we can see whether this hypothesis is sound or not. We've done many, many experiments since Monte Carlo. I report some of them here. I'm going to talk a little bit about LL5. I presented some information about LL12 in the poster yesterday. As you can see from this graph, is there a bigger pointer somewhere? As you can see from this graph, we've obtained very high, it's me, I'm blind. Very good loadings in some of our experiments, greater than 0.97, greater than 0.97. We've achieved those loadings, we've achieved high currents. We've obviously had durations. These are in days. We've run experiments for 84 days. I call attention to footnote 2. In general, cathodes begin to deload at current densities above approximately 100 milliamps per square centimeter. So we can attain the loadings, but we certainly haven't been able to maintain those loadings at high current densities. So we really haven't been very well able to test the hypothesis. Here's another set of experimental results to bring the table of the calorimetric experiments in our LL mass flow calorimeter up to date. More loadings, 0.96 or so. It's an electrochemical problem, I think. Loadings of 0.96, loadings of 0.94. None of the experiments on this particular table demonstrated any. It's a symmetry problem. None of the experiments on this table produced a discernible level of excess heat. Yet, we have separately met several of the conditions that I've described. We haven't jointly met those conditions. To show the difference between two experiments. This is a rather old experiment. Many of you will perhaps remember it. The colors don't come out very well, so I'll guide you through it. Two experiments, P16 and P15. These curves here are the resistance ratio on the right-hand side of the maximum. So we're looking at loading. According to our early calibration of the resistance ratio versus loading functionality. This P16 was loaded to something like 0.91. As we started up a current ramp, the loading increased. At some point, a very high current, 1.5 amps, 500 milliamps per square centimeter. This particular cathode started to deload. We lost some data in here, but the next time we observe it, the cathode is substantially deloaded. P16 evidenced no level of excess power. The calorimeter was in balance. P15 was somewhat better loaded as we started up this current ramp. And as the current increased, the loading increased, the resistance ratio came down, and this really attained a very remarkable level of loading, a loading of 0.97. Good, but better than that, it maintained the loading for substantial periods of time, many days, while the current was held at 1.5 amps. This is the sort of behavior that we're hoping to achieve. In more recent experiments, one of the experiments from the table that I showed you, we were able to achieve very similar levels of loading. This is a cathode. The current profile here is open circuit, small current, small current, small current, and then a current ramp going up to, in this case, 3 amps. As you can see, for those of you who are very familiar with this, cathode was deloading at open circuit. As we turned on the current, it loaded, went up over the resistance maximum, 0.727, loaded, it loaded, it loaded, it loaded again to a final loading level of about 0.96. Again, a spectacular value. But as we began to increase the current, hoping to produce excess power, very shortly in the current ramp, the cathode simply deloaded. It lost about 10% of its loading in a period of an hour or so. This is the norm. This is what we normally observe in 1996. It is not what we normally observed with our first lot of palladium in 1989 to 1992. As you can see, the calorimetry during this time is sensibly imbalanced. There's no significant level of excess power associated with this effect. So we really weren't able to test the notion at high currents, high loading, maintain it for considerable periods of time. Do we get excess heat? In this case, we couldn't meet our criteria. As a blow-up of that portion of the graph is actually set out on the same time window, 100 hours as the first graph. You can see the features that I was talking about. It was loaded to 0.927. We stepped the current up, it loaded to a value of about 0.95. I put this as a test on my poster yesterday, whether anybody would note this endothermic response and comment on it, and the only person that passed the test is Douglas Morrison. He watches us more closely than you think. The calorimeter goes into a small endothermic region due to the non-steady state response. As the power in the system is lifted up, the heat capacity required to be satisfied. The calorimeter shows a very small endothermic response, and the cathode vastly deloads from 0.97 down to 0.91, and then rapidly deloads thereafter and was not able to be loaded satisfactorily again. And this is a problem. This is a clear difficulty, this inability to replicate our experiments, one experiment to another. And I have here one of the clear imperatives in this field is the need to achieve replicability, or failing that, understand its absence. Why are the experiments not apparently replicable? We simply state we cannot replicate our experiments. We at SRI, at least, cannot replicate our experiments. And our strategy for performing our experiments is based precisely on the fact that we are not able to replicate. We start a farm of electrodes. We start 8 to 12 electrodes in identical calorimetric cells, put them to work in what we call a farm, and we simply select the ones which happen to behave well with respect to loading to put into our calorimeters. We expect not to achieve replicability. We've been beaten with this point: if an experiment cannot be replicated, it is not science. It's true. It doesn't mean that the experiment is bad or it's wrong or it's poorly performed or poorly conducted. It simply means that you must have replicability before you can use the scientific method to make progress. We've got two choices. Use another method other than the scientific method. I, for one, am not quite ready to do that. Or we can force the system to be replicable. Find the conditions sufficient and necessary to produce the effect, whatever the effect is and whatever the effect is due to, and learn how to control these conditions rigorously so we can do our experiments in a methodical and fundamental way. With due respect to my good friends Giuliano Preparato and Peter Hagelstein, I don't think that the principal problem in this field is coherence, its presence, or absence. I think the problem is a lack of coordination, and there are many people working in isolation with very little information interchange, not necessarily working on the things that they're best able to do. I urge, I plead for an increased degree of coordination between the various research efforts around the world. Amen. To coordinate, you must know the action of all others and contribute something original. I think that the work that's been started here at the NHE laboratory with sponsorship by Missy and Neto, under the rather wise guidance of Hideo Ikegama, the able leadership of Mr. Matsui and the direction of Dr. Asami, is a very good start in this pursuit of coordination. I'm going to terminate my lecture by asking you to applaud those gentlemen for their wisdom and perseverance. Thank you.
Thank you, Dr. Gilbert. We have time for a few questions. Yes.
Okay, Mike, in your first slide, you show that in your experiment, there is a constant endothermic region. So HFE is always negative. So it is very strange to observe, like positive. Why always negative? Where is going this energy?
Yeah, there is no endothermic region. The only endothermic region is the one that I pointed out and Douglas noticed. I mean, as I've said many times, whenever we see a departure from thermal balance, it's in a positive direction. We never see it in a negative direction. And I just showed you an example where that's not quite true, but it's very rare.
Almost not. You show that your energy balance is negative for a very long time.
That is
so
the
where do you think is going this energy?
You're talking about the non-steady state contribution on this curve?
More than 100,000.
Is that it? Yeah, and what's happening is that we're not doing this experiment under constant power control. The heater is turned off, so as the current increases and the power going into the calorimeter increases, the temperature of the cell contents increase. Because the temperature is increasing, we have to provide the energy which satisfies the heat capacity of the cell. So this is simply the non-steady state correction. This was the point of my poster yesterday. We understand it completely. It can easily be corrected for, but what I've presented here is the raw data. And if we took these to the non-steady state correction, this calorimeter would nail 0 within 20 milliwatts for the entire duration of this experiment, except for that. There is no heat capacity non-steady state correction needed or possible